Typically, when we think about the different phases of matter, like solid, liquid, and gas, and how they change from one thing to another, the way we think of them changing has to do with heat. Either we add heat to make the particles move faster and faster and spread out from each other, therefore increasing their kinetic energy and their potential energy, and that changes them into a solid to a liquid or a liquid to a gas. Or we do the opposite, we remove heat and send it back the other way, from a gas to a liquid and a liquid to a solid. But there's another factor besides the temperature, the kinetic energy of those particles, that determines whether we're dealing with a solid or a liquid or a gas. It's something that we often take for granted. It's pressure. Now, a lot of times in the lab, we have pressure being exerted on something, not from us physically pushing on it, but from the air that's just around us. Those little particles of nitrogen and oxygen, carbon dioxide and argon are constantly bombarding everything they run into, and that pushes on them. Okay? That pressure in the atmosphere is measured in a unit called atmospheres. Very creative. So a measurement of pressure around you just from the air is usually about 1 atmosphere. If we are therefore pushing like twice as hard as the air around you is, that would be measured as 2 atmospheres, and 100 atmospheres would be about 100 times as much pressure as what the air is constantly pushing around you. Okay? Now, because pressure is basically a force that is pushing on things, it kind of works against temperature in how something is a certain phase of matter. So when we crank up the temperature on something, we get the particles moving faster and faster and faster, which means they kind of head more in the direction of a gas. They try and get away from each other. So a higher temperature means particles can kind of move out more and more and more. On the other hand, a higher pressure means that we are constraining the particles more. We are forcing them together, so they're stuck near each other rather than being able to move around. So we end up with a graph kind of like this when we plot pressure and temperature in the same place. Okay? We would expect a solid, therefore, to have to kind of be there at high pressures and low temperatures. So particles aren't moving fast, and we are pushing hard on them to stay in the same place. That makes a solid. If we have a very high temperature, okay, and we have a low pressure, we're not really pushing on the particles as much, and they're just zipping around, we're getting a gas. All right, and in between, where we have kind of a balance between the pressure and the temperature, the particles move around quite a bit, but they aren't just free to move anywhere. Then we're dealing with a liquid. So on a graph like this, we call a phase diagram, because it's a diagram for different phases of matter. We have kind of these segments, or these sectors, these sections of the graph where we have a solid or a liquid or gas at different combinations of pressure and temperature. So here I'm going to kind of outline as best I can with a mouse where our solid is. Okay, so if we have a pressure and temperature combination that lands us in this kind of green wedge here, like 100 degrees Celsius and 40 atmospheres of pressure, okay? Or 300 degrees Celsius and 60 atmospheres, or 80 atmospheres and 0 degrees Celsius, or something like that, okay? That lands us in this kind of section here. That means we're dealing with a solid at that pressure and temperature, right? Our liquid is over here. If we have a pressure or temperature that lands us kind of in this little wedge in between the solid and the gas, we're dealing with a liquid. And again, bear with me, I'm using a mouse to do this. And if we have a pressure and temperature combination that lands us down here, that's farther down, over, down there. In this yellow section, we are dealing with a gas. Okay, so as long as that pressure and temperature combination lands us somewhere in here, we're dealing with a gas. All right. Now, these lines then are kind of separating these different phases of matter. So if I were to say, start with something at 300 degrees Celsius and 80 atmospheres, and I heat it up, I crank the temperature up, so much so that it crosses this line, I would be changing from a solid into a liquid. Okay, and that's kind of a familiar thing. We add some heat, we get the temperature rising until we pass from a solid to a liquid, and we do so by crossing this line here. Okay, well, temperature is not the only way I could do that. I could also say start at 90 atmospheres and 400 degrees Celsius, okay, and then while keeping temperature constant, in other words, my temperature side to side doesn't change, I'm only changing the pressure. I decrease the pressure going this way, I could change from a solid to a liquid also. I would just end up crossing the line through here. So it doesn't really matter where I cross this line, as long as I'm going across the boundary from the solid to a liquid, it's the same phase change. Okay, and we already have a name for that phase change. When we go from a solid to a liquid, we call that melting. I don't trust myself to write this out with my mouse, so I'm going to try and add in some text. Let's try size 32. Yeah, that should be good. Change it to, let's get a darker color of red. Yeah, there we go. Melting. We got our melting here, going from a solid to a liquid. Okay, which means if we go in the opposite direction, from a liquid to a solid, again, any way we cross this line, we're going through that phase change, okay, which we already have a name for. If we go from a liquid back to a solid, we call that freezing. Put it somewhere where it's not going to be in the way. That might be the best I can do. Okay. I can continue this for the liquid and the gas. Some other familiar changes. If I go from a liquid to a gas, we call that boiling. Oh, let me change my text to red. Stick out a little better. Oh, it's underneath the, put it kind of up here. So boiling is going from liquid to gas. And if I were to go the other way around, and go from gas back to a liquid, well, that's the opposite of boiling. We call that condensation. That's condensation right there. Okay, now these four phase changes we are pretty familiar with by this point. Okay, it's kind of something we've seen already before. But we also have the potential for a new set of phase changes, where we go between the solid and the gas and the solid, back and forth there, without having to do the liquid in between. Okay, that means it's not really melting, okay, or it's not really boiling. It's not really condensing and freezing put together. Okay, this is a totally different phase change that deserves its own name. Okay, and actually it's two different phase changes that deserve their own names. To go from a solid straight to a gas with no liquid in between, we call that sublimation. Something sublimates or sublimes. It goes straight from a solid to a gas. This is something that dry ice does. It's something that mothballs do. We call it dry ice. It's just solid CO2. We call it dry ice because there is no liquid in between. It goes straight from the solid to the gas. And you can use it for all kinds of great fog effects on stage, especially for like rock concerts and stuff. Going the other way, from a gas straight to a solid, we call that deposition. Okay, and this one's a little bit easier. If you leave off the end, it's just the word deposit. So it's kind of like we're depositing a solid out of the gas. Okay, so that's deposition, going straight from a gas to a solid. You'll sometimes see this in the wintertime when you have these really nice ice crystally patterns that show up on the windows of your car or of your house. That is from water directly just being deposited from the air straight onto the glass without first condensing into a liquid first. That's why we get those really cool patterns. It's not just a drop of water that suddenly froze. we go straight from the gas to this wonderful crystal pattern of ice on the glass. Okay, so we have a total of 6 phase changes, 2 of which we would never see on a heating curve or a cooling curve, which is pretty interesting. Now, on a heating curve and a cooling curve, we had sections where we had an equilibrium, like during the melting process or the freezing process or whatever kind of phase change we were looking at. We had a flat section where we were in the process of going from a solid to a liquid or a liquid to a gas or back the other way, and we were kind of riding on this flat line. We have those here too, okay? And they are these kind of lines in between. Whoops, let me change to a different color. Okay, there are these lines kind of in between each of these phases of matter, kind of here and here and here. So if you were to land directly on one of these lines, like right there, or right there, or right there, something like that, somewhere on that line, okay, you would have an equilibrium between the 2 phases of matter that you're kind of straddled between. So like being right here, a pressure and temperature that landed us right there, okay, would mean we have an equilibrium between the solid and the liquid. Okay? If we were at a pressure and temperature that got us right here, okay, we would have an equilibrium between the liquid and the gas. Okay? Now, this tells us something very interesting. There is a point where all 3 of these lines meet, which implies we can have all 3 phases of matter in equilibrium at the same time, which is pretty crazy. We can have all 3 phases of matter coexisting with each other. Okay? We call this point, this one combination of pressure and temperature, the triple point. Let me decrease my font size a little bit so I can fit this in here. Let's change to purple. Triple point. Where we have a solid, liquid, and gas in equilibrium, all together at once. Okay, and again, that's that one point where all these lines connect together. Okay, so we can have an equilibrium between any of these phases of matter, but also between all 3 at once. And this is something you don't see unless you're looking at a phase diagram like this. Okay, again, we call that the triple point. And that's just where we have all 3 of those phases of matter in equilibrium together. Okay, so in an assignment with something like this, we might be asking questions about whether you have a solid or liquid or a gas at a certain combination of pressure and temperature. Kind of play battleship with it and kind of figure out where you're landing on there. You might try and figure out what phase change you're going through as you change temperature, okay, but keep pressure constant, going like across this way, or you change pressure but keep temperature constant, like going this way up and down, okay, or you have a combination of temperature and pressure changing at the same time, kind of going in a diagonal somehow, okay.